right, very good afternoon, everyone. Thank you for attending my talk at the AIAA SciTech conference. My name is Sam Low. I'm a PhD student at the Stanford Space Rendezvous Lab, and I'm advised by Professor Sumaya Diamiko. Today, I'm going to talk to you about how we are developing flight-ready, precise, and robust carrier-phase GNSS-based navigation software for future distributed space system missions. So differential GNSS is now widely considered for emerging formation flying missions. Historically, differential GNSS with integer ambiguity resolution was used mainly for ground post-process solutions, and it was until 2010 that Prisma demonstrated the first in-orbit differential GNSS with float ambiguity estimation in real time. In future, missions such as VISERS will demonstrate real-time onboard IAR. Our paper presents a comprehensive survey of past and upcoming missions proposing the use of differential GNSS. Many of them include the use of IAR. These missions span distributed space telescopes, star shades, X-ray observatories, etc. And from this, many overlapping navigation requirements were actually identified. First, real-time onboard IAR is a shared proposed requirement across many of these missions that wish to incorporate sub-centimeter level inter-spacecraft alignment knowledge as part of their requirements. And this is made only possible with IAR. Two other important points are that of robustness. Navigation has to be robust to cross-link outages, latencies, measurement errors, and anomalies. And finally, all of navigation must remain performant within the tight computational and memory limits of the flight computer. This work makes 5 technical contributions. First, we perform a survey of contemporary missions using differential GNSS, and we propose a unified set of navigation requirements. This provides traceability and also anchors the design of our flight software. Within our flight software architecture, we propose a new numerically stable form of the consider common filter with improved orbit prediction accuracy. A fault detection, isolation, and recovery module is also developed in this work using a purely memoryless and statistical outlier detection algorithm. This is all wrapped within a modular callback-based flight software design for ease of integration into any wider GNSS host software that is written in C++. And finally, we will introduce the test bed design that was also developed in this work so that we can verify our system against the proposed requirements. Altogether, these contributions deliver a requirements traceable navigation package that has been comprehensively validated for flight. Here we present an overview of the identified requirements according to interfacing, functional, and performance. Interfacing basically provides the reader a checklist for how navigation should exchange data with the subsystem. Functional requirements define what navigation must do qualitatively, while performance requirements set how well the system operates in each of its navigation modes quantitatively. Robustness margins are also specified within the paper. A key concern that is not well addressed in literature, especially in formation flying, is the handling of uncertainty between center of mass to phase center offsets errors. Typically, the spacecraft states, which we show our state vector here, takes reference from the spacecraft center of mass, as that is what the control usually references. However, GNSS measurements originate from the antenna phase center, which is shown in these cylinders on the diagram here. And typically, we know what this offset is from pre-flight measurements or from a CAD model. But errors may still arise in flight due to variations in body frame mounting errors, variations in the center of mass, or phase center variations over time. And so under millimeter level alignment, these effects could become significant, and so we treat them as consider parameters in a consider common filter. This allows the impact to be propagated without attempting to estimate these errors, which are poorly observed. Prior to filtering in our architecture, the interfacing layer collates all of this information, which includes ephemeris, measurements, attitudes, and maneuvers, and delivers them in a time-ordered stream to the filter. If no remote measurements arrive due to a crosslink outage, the interface layer actually has a decision logic implemented that will help trigger transition into and out of absolute only orbit determination. The filter expectantly propagates and updates the states, including all float ambiguity estimates prior to integer resolution in the IAR block as seen on the bottom right. IAR is based on a well-known lambda method developed by Professor Peter Tunison, but within its implementation, we actually follow the modified lambda, which was developed by Professor Chang Xiaowen for efficient computation. All this time, there is an integrated fault detection, isolation, and recovery module, or called FDIR, that screens measurement residuals for anomalies. For the filter design, we identified two potential points of numerical instability with the well-known minimum covariance form of the considered common filter. First, when computing the innovation covariance in this form, the sum of transposers results in a symmetric but not necessarily positive definite quantity. And in theory, the innovation covariance should be PD, but in practice, we have observed that when computing the innovation in this form, numerical errors could cause non-PD in very rare isolated incidents. This is catastrophic mid-flight because if the inverse of the innovation does not exist, then your common gain cannot be computed. And to remedy this, we basically provide an extra regularization term that guarantees the existence of the inverse. The algorithm is in the paper. We encourage you to read it. The second step is that we actually refactorize the well-known measurement update step into a Joseph form, which provides a theoretical guarantee for positive definiteness. To our best knowledge, the Joseph form of the considered common filter has not really been discussed in literature, nor has it been trialed in slide. And so this presents itself as an opportunity for technical contribution as well. To evaluate this newly applied Joseph form of the considered common filter, we actually ran 10,000 Monte Carlo trials for a variety of measurement updates, initialized using extremely ill-conditioned Hilbert matrices as the initial covariance. And we use randomized sensitivity matrices for the measurements as well. No process noise was added, and expectedly, the Joseph form in blue runs into much less non-PD cases as compared to the non-Joseph form, and hence it performs better as expected. We also developed a correlated analytical process noise model for relative dynamics in Cartesian space. This is built on the insight that nearby spacecraft in proximity should experience correlated perturbations. And this means that within the filter, any modeling errors in gravity, drag, or solar radiation pressure, etc., the errors should also be partially shared. And so we define a spatially correlated spectral noise dynamics spectral noise density matrix, which is propagated to yield the full process noise matrix that reflects these dynamics correlations. This produces realistic and significantly more accurate relative orbit predictions during data gaps. And we'll see, and we will present how we will show that it is essential for meeting the open loop orbit propagation requirements. Next, this block diagram actually summarizes how the fault detection, isolation, and recovery pipeline works. Prior to FDIR, all data is screened for health and anomalies at the interface layer. And then what we do is we actually apply a memoryless estimation of the distribution of prefit residuals. And we use our knowledge of this distribution to do outlier screening. The implementation is done in a purely memoryless way. And so this is suitable for flight because no samples need to be stored on board. Again, full details are in the paper, but in this presentation, we will assess the performance of FDIR. Let's talk a bit about the actual software implementation. Although the flight software is written in C++17, the code can be cross-compiled and executed natively with standard C libraries on our embedded flat sets. On the left, the host is provided a well-defined set of input functions in the header file. And this includes inputs such as attitude, GNSS messages, maneuvers, and cross-link data. On the right, the host is expected to inherit a class which defines a set of callbacks. This includes type callbacks for timing, logging, cross-link outputs, callbacks with state estimates, and status bytes. To highlight a few key features of this software design, first of all implementation details are hidden behind a clean header file for encapsulation purposes, and this simplifies integration and reduces compile time dependencies for anyone who's looking to integrate navigation within a wider GNC. Second, the callback-based design allows not only for ease of integration, but it allows the host to customize its response logic whenever a callback is made from navigation. Third, race conditions are prevented using only a single thread with lock guards, and this helps to preserve state integrity throughout flight. Our navigation software also features a lot of computational optimizations, two of which are the most impactful. First, we minimize computational costs by exploiting sparse matrix operations whenever possible. Second, we observe that a large amount of compute time is actually spent handling the large covariance matrix, especially with the sheer number of float ambiguities to estimate. So to fix this, what we actually do is we resize the covariance matrix dynamically in flight. And this is possible because upon IAR, any fixed integers can be treated as known constants instead of state variables in the state vector. And this allows us to resize the covariance to include only the active indices. This results in a significant reduction in compute time. Okay, so we've presented architecture and algorithms, and now we're going to put our work through a structured test campaign that we're going to draw on from the VISERS mission. For introduction, VISERS is a distributed space telescope mission that flies 2 6U CubeSats that you can see in this image here. And what they're trying to do is to synthesize a larger aperture for imaging the solar corona at high resolutions. So the detector spacecraft on the left actually hosts a detector payload, a sensor payload, while the optics spacecraft hosts a photon sieve that acts as a lens to focus the image. Applying our navigation requirements analysis in a paper devices, we derive these performance requirements. And perhaps the most critical performance requirement is that of during science, where we are doing actual observations. The optics spacecraft needs to maintain a controlled 40-meter separation with millimeter level lateral alignment and plus minus 15 millimeters of focal length tolerance. Requirements for tolerance margins are also quantified in the paper, and these refer to undesirable conditions that could arise in flight that we have to guard against. Now we summarize the test campaign that we did in this work. We map compliance tests to individual requirements for traceable verification. Down each row, it represents different levels of testing fidelity. We will present in today's presentation software emulated nominal conditions, degraded conditions, and contingency cases before presenting the full campaign results using real-time hardware in the loop with a GNSS receiver as well as a controller in the loop. Overall, this matrix summarizes in a very compact way how we execute our traceability between tests and requirements. But before diving into the results, it's very important to know how the truth and the flight models differ in our tests. The truth dynamics generally have much higher order perturbations, and we deliberately make a distinction between the ground and truth. So the flight dynamics the filter flight dynamics have a suppressed fidelity as compared to the truth in order to stress test the ability of the filter to accurately do orbit prediction. Ground truth measurement modeling adopts broadcast-like signal and space errors, while user-side errors adopt the full VISERS antenna gain pattern profile. One thing that we really wanted to stress test was that we injected a poorly observed 5 centimeter phase center offset bias, but we've set the considered covariance to assume only a 5 millimeter uncertainty. We deliberately create this mismatch to see whether the filter is robust to any large anomalous offsets that are not accounted for. The ground truth dynamics measurements and body frame models are all exercised in a software in the loop setup where a high fidelity ground truth simulator actually feeds GPS measurements into each instance of navigation. So each of those green blocks actually represent navigation running on a flat set. On the client computer, the ground truth simulation then emulates cross-link between each of the flat sets, as well as control responses if there are any maneuvers. And for the initial software-only test, we will adopt just the VISERS standby relative orbit, which is characterized by about 400 meter long track separation with a 200 meter passive safety margin. The absolute orbit is 500 kilometers in sun-synchronous orbit. So now let's finally dive into some of the navigation results with some ablation studies. Nominally under well-behaved operating conditions with integer ambiguity resolution, we do meet the requirements, and the requirements stated out for visors are on the gray dashed line. So this is sub-millimeter per axis, and IR achieves a 99.7% correct resolution rate in this particular scenario. Notice that we did inject a very large phase center offset, but the state error remains largely unbiased. And this desirable result arises because the filter does have sufficient degrees of freedom in the state vector to absorb any residual biases. And any center of mass phase center uncertainty that remains is correctly carried through the considered covariance, so its impact is still accounted for. This is evident as you can see that the covariance envelope hugs, the 1 sigma covariance envelope hugs this true state error as shown. When we increase the measurement thermal noise up to 300%, without accounting for this equivalent increase in the filter measurement model, we see that both relative positions and velocities do exhibit higher noise, but they more or less remain performant within their requirement bounds. And if we switch off integer ambiguity resolution, or in the case where integer ambiguity resolution fails, we fall back to the float ambiguity resolution solution, which is about 10 centimeters, 1 sigma in the radial tangential axis, and about 5 centimeters in the normal axis. Velocity requirements are still being met, as you can see on the rightmost chart. Next, for one of our stress tests, we introduced repeated cross-link blackouts where differential GNSS is no longer possible. Each blackout lasts for about 95 minutes or 1 orbit period. In visors, the requirement that we've set up for the terminal relative state error at the end of the cross-link outage is less than 1 meter in relative position and less than 5 millimeters per second in relative velocity, just using open loop orbit propagation. But the important takeaway here isn't that we have met this. It's not that we have met this requirement, because the error itself can be influenced by your initial state uncertainty and also the disparity in modeling between your truth dynamics and your filter dynamics. Rather, the key insight that we want to present in this slide is the role that correlations play in the process noise model. So we repeat the same scenario, but this time for just 1 dedicated blackout, or again for 1 full orbit. On the top, it shows the case where the correlations are not captured, and the bottom where it includes correlations in the process noise model. We see relative orbit predictions diverge dramatically. And so the takeaway is that it is indeed essential to preserve the true covariance structure between the 2 spacecraft through a physically consistent process noise model that reflects the dynamics correlation. Finally, we run a contingency case where we actually inject cycle slips on all channels once every orbit. So we'll examine how FDIR performs in this case. Cycle slips are modeled by corrupting receiver carrier phase measurements with large discontinuities that are independent across all channels. FDIR triggers a fault response due to the high number of out-of-distribution outliers that exceed the concentration inequality bounds. Recovery is executed immediately, and we see that the net impact on navigation is that you have a few minutes of outages. You have a few minutes of incapability where the navigation filter is trying to recover, and subsequently, once it recovers, it's able to regain the solution without breaking the covariance envelope. And so we are still estimating, the estimates are still healthy. And this result is consistent and reproducible for all cycle slips in this scenario. Finally, we're going to put navigation under the ultimate stress test, an actual real-time hardware in the loop test bed. So we use an iPhone Nova Plus as our source of GNSS signals. The whole setup is closed loop with a controller and a maneuver planner which actuates the ground truth trajectory and feedbacks the maneuvered trajectory back into the iPhone so that the signals emulate the controlled trajectory. This is a quick look of how the actual experimental setup looks like. Of interest to note is that we are using near exact representations of the onboard flight hardware of visors. This includes the flat sets and the GPS receivers. All software-only emulations are done so to the same fidelity that was presented earlier. And for brevity now, I'm going to just skip ahead to the real-time hardware and loop results. So here we see that the leftmost plots on the top left are the ground truth relative orbital trajectories, and on the bottom left are the estimated relative orbit trajectories. We have the relative position errors of one spacecraft with respect to the other for both spacecraft, and this is piped out directly from filter telemetry. The vertical red bars represent executions of maneuvers, and the bottom plots show the evolution of the relative orbital elements. Of interest to note is whenever you see that there is an opportunity for alignment, we also model how the laser rangefinder scatters that is emitted from one of the spacecraft onto the reflector panel of the other spacecraft. So you can actually see the laser rangefinder scatter grouping on this plot as well. Visors, this campaign lasted for about 2.5 days. So a full visors campaign is about 35 orbits. So that's about 10, which includes 10 orbits of science in the middle. Finally, run times are assessed from the real-time hardware loop campaign. And these are runtimes on the flat sets themselves, and so they are representative of the actual visors computers. They are assessed with between the current considered common filter that we developed, as well as predecessor filter architectures that we have tried before. And we are able to complete a full state estimation loop in under 50 milliseconds for the Joseph form on average, and under 5 milliseconds on the non-Joseph form. Bearing in mind that the hardware that we're working on is 2016 hardware that's running, it's an ARM P7 architecture, and we're running pretty old hardware basically. In conclusion, we identified navigation requirements in this work, and we applied them to emerging distributed space system missions that leverage carrier-based differential GNSS. We demonstrate its performance on high fidelity test bits, and with upcoming on-orbit validation missions such as VISORS and SLARI, we aim for these lessons learned to directly shape the next generation of formation flying missions, so that we can close this learning feedback loop and share it with the wider community. And with that, I thank you for listening to my presentation.